Okay, so in this section, we'll be looking at conditions in which we can find power series solutions of a differential equation, second order differential equation. So suppose we have some second order differential equation equal to 0. So a point x equals c is said to be a ordinary point of the differential equation if the p of x and q of x, so the p of x is the coefficient function in front of y prime, and q of x is the coefficient function in front of y. So if they're both analytic at c, and what we mean by analytic means that you'd have a power series representations centered at x equals c. So that's an ordinary point. Then we say that the point is not if the point is not ordinary, is said to be a singular point of the differential equation. So let's look at some examples. Okay, so an example find any singular points for each differential equation. So say A, we have y double prime plus 3xy prime plus e to the x y equals 0. Okay, so the 3x would be my p of x, and the e of x would be my q of x. Okay, so my p is the 3x, my q is the e to the x. So note both p of x equal to x and q of x equal to e to the x are analytic for all x. So, well, polynomials are always going to be analytic. So p of x equal to x is just a polynomial. So automatically that x we can consider as the power series. And e to the x, recall it has a power series that converges for all x. So let me write the power series for e to the x here. So recall the power series for e to the x is summation x to the n over n factorial, and this converges for all x. So hence the differential equation has no singular points. Okay, so let me do another example. Some out of space, so let me erase a few things and we'll do part B to this example. Okay, so here's part B. So we define any singular points here. So the first thing to do is write it so there's a 1 in front of the y double prime. So let's divide by x. So doing that we get then. So dividing by x we get this then. So this would be my p, this would be my q. So let me write that here. Okay, so our p is 7 over x times x minus 1, and q of x is just x. So q of x would be analytic for all x, but the p equals 7 over x times x minus 1 is not going to be analytic pretty much where you're dividing by 0. So it's not going to be analytic when x is 0 and when x is 1. So let's note that. So p of x then is not analytic, so it's not going to have any power series representation at x equals 0 and x equals 1. So hence x equals 0 and x equals 1 are singular points of our differential equation up here. Okay, now let me state a theorem. Okay, so here's a theorem. I'm not going to prove it, we're just going to state it here. It says if x equals c is an ordinary point of the differential equation, then we can always find two linearly independent solutions of the form, so pretty much power series centered at c, which converges on some interval around c, where the distance between c, the center, and the radius here is the closest singular point. Okay, so that's a radius convergence would be the closest singular point to C. Alright. So this theorem only involves ordinary points. So you might say, well, what if I have a singular point? Can I not find the power series representation for the solution? And the answer is not necessarily, but we can get close to finding a power series. That's what the next part that we're going to talk about now is going to talk about how we can almost find the power series representation for these singular points under certain conditions. Okay, so I'm out of space here, so let me erase a few things and we'll keep going. Okay, so a singular point x equals c is said to be a regular singular point of the differential equation if x minus c times my p function and x minus c squared times my q function are both analytic at c. And a singular point that is not regular is said to be an irregular singular point. So if you go back to our last example that we just finished, we showed that x equals 0 and x equals 1 are both singular points. But now, let's test it here. Let's go x minus c times my p. My p here is the 7 over x times x minus 1. Let's go then, let's check our x equals 0 point. So it'll be x minus 0 times p. So the x will cross off the x here and becomes 7 over x minus 1. And this actually does have a power series representation at x equals 0. So you're not dividing by 0 anywhere at this point. So it's analytic. I'm not checking q here because q of x equals x is already analytic. So there's no need to check that condition in this case. And checking the x equals 1. So if I look at x minus 1 then, so my x minus c times my p, x minus 1 will cross off with the x minus 1 here. It'll become 7, actually it should be 7 here. 7 over x, and this is analytic at x equals 1. So therefore, hence both x equals 0 and x equals 1 are regular singular points. If I wanted to get an irregular singular point, I could maybe put a square on the x there. So if I added a square there, say, that had been a square, then when I multiplied by x, there'd still be an x left down here, and it would not be analytic in that case. So pretty much multiplying by x minus c times my p has to get rid of the dividing by 0 point at the bottom. So I'd have to cross off an x minus c in the bottom to be regular. And it does in this case, but again, if this had to be into a higher power here, like a 2, then this guy would not be analytic, and then x0 would be an irregular point if that was the case. Okay, so now we're going to look at a theorem about finding power series. Well, it's kind of like a power series representation solution for this differential equation when you have regular singular points. It's called Frobenius's theorem. So let me state it. Okay, so here's a theorem. We refer to it as Frobenius method. So then after Frobenius, we came up with it. So if x equals c is a regular singular point of the differential equation, then there exists at least one. So notice here is not saying 2 necessarily, so you can define at least one solution of the form. So it looks like pretty much like a power series here multiplied by x minus c to the r. This r could be a fraction up here. It's some constant that we have to determine. So you can see if I took that part away, that part right there is a power series. So multiplying it by this, it's no longer a power series, but it's similar to a power series. So you can write it like this. So we have to find the r value. And this series will converge on some interval here, 0 less than x minus c less than r. So we can find at least one series solution that looks like this. This is the method of Frobenius. And we're going to apply this and some examples to find some series solutions. But I'm not going to do any in this video, so I'm going to end the video here. So in the next couple of videos, we'll do some examples using Frobenius method to find these series solutions. Okay, so let's leave it there.